on everybody's door.
All right, notes out. You guys also need to come grab a ruler. One person each group, please grab a ruler.
My own projection.
One per person. Kind of work the first one together. It says the focal point of a concave mirror is 5 centimeters. An object is placed 8 centimeters from the mirror. Use array tracing and lens formula. What is the image distance? Now when you do this, remember, you only have to do that because you have a ruler. The reason mine has all the little lines on it, because I don't have a ruler that goes on here. So the lines are my ruler. You just have to make basically a cross. And how do you set this up? Well, first let's think about this. Where is the object in relation to the focus compared to the mirror? Is the object closer to the mirror than the focus or farther from the mirror than the focus? Farther. And since it's a concave mirror, that means what kind of image? Real. It's going to be a real image. Basically, if the object distance is larger than the focal point for a concave mirror, it's a real image. If it's smaller, it's going to be a virtual image. Convex mirrors are always virtual. So remember, for virtual images, you kind of want to make your line in the middle. For real images, you kind of want to make it at the end. So you would just here, you want to make sure you get this very even like that. You want it make sure they're very perpendicular. And remember, I just like to remind myself what kind of mirror it is, I do that. But we draw all our lines to the perpendicular line. So I say I measure out my ruler from the mirror 1, 2, 3, 4, 5. Well, there's the focal point. That's F. Then 1, 2, 3, 4, 5, 6, 7, 8. There's my object. O. There's my object. Now you're going to follow those rules. I gave you a couple of class times ago. You're going to follow those rules. Remember, 3 lines. Parallel to the focus and parallel, and at the middle. So right now, try to make your lines. Try to make your lines. Using your lines, try to find what is the distance on that. And remember, is my image going to be erect or inverted? Inverted, so I should expect it to come out on the bottom of the line. All right? Yes, ma'am. So we have our lines. So the first line is always drawn parallel to the axis. The black line is the axis. And any line that's parallel to the axis will go through the focal point. Any line that's parallel to the axis will go through the focal point. What? The object, yeah. We usually draw from the top of the object, whatever the object is on that. Second line it goes through the focal point. Any line that goes through or from the focal point will come out parallel to the axis. And so they intersect right there. So that would be my image. And I go, let's see, so, well, this is 8, 9, 10, 11. So by my ray diagram here, I got 11 centimeters. There, our third line is the check line. The check line, we go to the middle, comes out at an equal angle, like that. 3 lines, parallel to the focus parallel, and then it hits the middle. We use the law of reflection. Angle in equals angle out. That's our check line. It's the first 2 lines that really decide where it's going to be, lines 1 and 2. Now, so that's so you should have gotten somewhere within that ballpark. The big things here is, 1, not drawing your line parallel. Actually, that's what's going to throw mine off because my line isn't, or these 2 aren't perpendicular on that. Also making sure your lines are parallel and that sort of thing. All right. So, but we've only done the first half. Remember, it says by tracing and the lens formula. So we have to do it by two ways. Now remember, our lens formula is 1 over the focal length equals 1 over the object plus 1 over the image. That was that lens equation. So in this case, 1 over 5 equals 1 over 8 plus 1 over I. And we'll come back to this in a second. But there's a couple of notes you need to add. When you are dealing with mirrors, and lenses, there are positive negatives, but for positives, positive in front, negative behind. Object distance is always positive. It's always in front of the mirror. Focal length. Focal length will be positive for a concave mirror, which is what we're using right now. And it's negative for a convex because the focal point appears to be behind the mirror. The negatives are virtual. Image distance. Positive, real, negative, virtual. If you don't apply these signs, you will not come up with the right answers. Now for this question, all the values are going to be what?
Positive.
Positive. Positive focal length. We have a positive object distance, and since it's a real image, we should have a positive image distance. All right? Anyone need more time on this? It should be in your notes somewhere. Yes, sir.
I need more time.
We good?
Yeah.
So we go back to our problem here. I get 1 over I equals 1/5 minus 1/8. 1/5 minus 1/8. I usually just use my inverse key. I don't worry about finding common denominators. You know, it's like 8/40ths minus, 5/40ths, and I get 3/40ths. And just make them decimals and do it in your calculator. But remember, inverse key. Usually the inverse key is one of these two ways. Most calculators, it's an x to the minus first. Now sometimes it's its own key. Sometimes it's one of those second keys. Or sometimes you get INV. Some calculators use inverse. X to the minus first tends to be the most common way, but your calculator is your calculator. You should know which one it is. So if I go on this, I go 5 inverse minus 8 inverse, and I get 1 over I equals 0.075, which is actually 3/40ths. That's what 3/40ths is. Am I done?
No.
No, I need to take the inverse of that answer, which comes out to be 13.3 centimeters. 13. Now I got about 11.
12 and a half.
Anybody get a 13? 13, anybody get 12? 12 something. 12 something. 14 something? 18? That's a little off.
Just a little bit.
Yeah, usually when I grade these, I look at how are you within the ballpark. Okay, I look to see, also look at your lines and things like that. Where you're in the ballpark. All right, so questions on that? Okay, let's try another one. Focal point, now I want you to do ballpark before we go over this. A focal point of a concave mirror is 2 centimeters. An object is placed 5 centimeters from the mirror. Using ray tracing in the lens formula, what is the image distance? So again, make a prediction. Is this going to be a real or virtual image?
Real.
Real because the object distance is bigger than the focal point. All right, so you guys draw in your line. By the way, when you do these real images, I would just put the line way down here. It gives you lots of room to work with. Is done.
That's very unnot, yeah.
No.
So, cricket.
Redo it. Redo it. It's gonna mess up the whole project.
So long.
No, it's not straight. No.
Well, those lines over there are not straight. There you go. That's perfect.
No.
There. Anyway. All right, so we have our focal point, which was 2 centimeters. We have our image, which is at 5 centimeters. So there's our O. So we have parallel through the focal point, through the focal point, and parallel. So we end up with a, about right there. Yeah, my line's a little off.
Mine's off. So I just hitting that.
Let me see. Sometimes it's hard to see where exactly you are.
No.
A little better. All right. So, boom, about right there. Yeah, that looks better. So there's my image. And my image looks to be about 3.5 centimeters.
Yeah, mine was 3.1.
All right, so by formula, remember 1 over F equals 1 over O plus 1 over I. So I have 1 over 2 equals 1/5 plus 1 over I. So I get 1 over I equals 1/2 minus 1/5, which is 0.5 minus 0.2. So 1 over I is 0.3, which means I is 3.3333333 centimeters. So 3.5, that's not bad. So somewhere around 3. But notice this time the image was between the focal point and the object. Don't anticipate. Basically, if the object were at the focal point, you're kind of like at an infinite distance. This is where the image. And as we pull back on our object, the image moves in. And basically, they pass each other at the center of curvature. I think that's where they pass each other, which is twice the focal length. So if we were at 4, they'd both be at the same spot on this particular one. But once the object gets beyond 4, that's going to be inside. And when this gets infinitely far, it's going to be at the focal point. That's how that works. So they kind of move. So don't, just because it ends up, it's going to be somewhere. Basically, if you ended up inside the focal point, that's when you need to start to worry. You end up inside the focal point, that's really time to worry, because a real image should not come inside the focal point. Okay, that's it for today. We'll do another one next time on that. So, we need to take some notes because we got to get to a certain point in order to do your concept builders by the end of the period. Otherwise, you have to take them home for homework. Okay. So, remember we're talking about refraction. Remember, light refracts. And if anybody's ever gone and tried to grab a fish in the water, they know that they grab the image of the fish, it's not going to be there. Because it works the same way the reflection. Remember about the reflection, the reason we think the image is behind the mirror is because our brain thinks all rays come in what kind of line? Straight line. Chris, are we having a problem?
No, what makes you think we're having a problem?
Because you're not looking up here.
So it looks higher? Like
Yeah, it's going to look higher because notice the light coming off the fish This is water going into air. There's our angle of incidence. Angle of refraction is going to be bigger. It bends away from the normal. But remember, your brain thinks all rays come in a straight line, so it appears the fish is going to be higher. This fish is higher. So if I grabbed at the image of the fish, I'm going hungry.
So if you want to grab the fish, like
I need to grab
you gotta go even
below. In other words, you're going to aim basically in front of the fish. It's like if I was spear fishing. If I had a spear and I wanted to spear this fish, am I going to aim above the image, at the image, or below the image? Below. Yeah, I'm going to kind of aim in front and below the image. But I have a question. What if I had this brand new laser fish getter? No, it's a fish getter. In other words, it's like kind of like shoots the fish with a laser and it floats to the surface. Where am I going to aim now? Am I going to aim above the fish, at the fish, or below the fish?
above the fish. Above.
How many of you say above? How many of you say at the fish? How many of you still say below? Well, let's think. A laser is what? Light. Well, if the light from the fish followed this path, if I fire the laser, if I fired the laser at the fish, the water's going to bend it and it's going to go right to the fish. Remember, the spear is a physical object. It's not going to bend when it hits the water. Although it appears to bend, you ever stick a stick in the water and it looks like it bends. There's a refraction. But it's not going to bend because it's in there. But the light ray will bend. This is the difference. Now keep this idea in mind because there's a thing in your concept builders that kind of deals with this. It kind of goes along with that on there. So think about that. Same reason like a depth of a block. And they have a picture in your book. If you had a book, if you were on like page 452, this is the same idea. You have a big glass block. A block of glass looks like it's actually thinner than it really is. Appears to be thinner. This is why when you get that big mug of root beer, you have those real thick glasses. Does it look like it's the root beer is all the way to the edge of the glass? Yeah, if you look at the glass, it will look like it goes all the way to the edge of the glass. When we look down to the top, there's only this little tiny hole in the top. Looks like this great big glass of root beer, and you have this little teeny tiny thing because the light refracts around the outside.
Why do they do that to the chips?
Do that with what?
The chips, they fill it like half the bag with like egg.
That's weight. It makes it look. I'm not a marketing guy. Which leads us to atmospheric. Now this is, we've talked about water and glass. Light in the atmosphere. Now mirages. Mirages.
Like in the desert?
Well, it can happen anywhere. If you're out and you're lost in the desert and you see a water cooler, that's not a mirage. That's a hallucination. You're dying.
Oh, you just see water.
Mirage. You've all seen a mirage. How many of you have been driving down the road and it looks like way out in the distance there's water?
It's like waves.
Water. That's a mirage because what you're actually seeing is the sky. When you see that water and it looks like there's water on the road way out there, you're actually seeing the sky. The light from the sky is being bent to your eyes. That's it. And why is it wavery? Well, let's think, this is hot air rising. Is hot air rising going to be nice and smooth? They're all kind of rough and roily. Rough and roily. So it gives it that image, that shimmering image. That's the mirage.
So how can you tell if it's really a mirage while you're driving or if it's not really water?
Well, I guess when you get to it, it's still there when you get to it, it was water. But remember, the mirage is going to keep moving in front of you. It's going to dissipate as it keeps moving in front of you.
So the desert.
Now, you see this more like on concrete. You might get in the desert, you see it more. In the desert, you might see, the reason they would see it is like an oasis. There'd be an oasis, and they would see that. But notice, the light from our palm tree is being bent so it's upward and against that whole straight line thing, right? Our eyes think it's straight line. But notice the image appears to be upside down. What happens, we'll usually see is the sky. This light from the sky, so here's the blue sky, gets bent up to our eyes and we see it down on the ground, and so it looks like that shimmering. In fact, if you have a book and you turn to page 482, if you have a book, turn to page, actually the picture's on 483. Look on that picture on page 483. I see a couple of you with a book. Look at the picture. There's a bunch of cars there. You can see what looks like water, which is sky. What can you see under the car on page 453? Did I say 480? 453, sorry. I can't, numbers are too small. Page 453. On page 453, look at the cars. Look underneath the car. What do you see? You see an image of the, well, I see an image of the sky, but I also see an image of the car. But it's upside down. It's like the car is driving on top of its image, because you're seeing that image. This is actually a very strong mirage. But notice, on the areas on the side of the road where there's like ground and trees, notice there's no mirage, because it's not as hot. Remember that concrete gets extremely hot, much hotter than the ground on that. Okay, can we put the rulers down? All right, but you can see how close up there's no mirage, but farther out you have the mirage, and the mirage keeps moving into a certain place. Notice if you look at that picture way beyond, there's no mirage. It's only this one central band, which is at that right angle for you to see on that. What are you guys doing? That was from last class. They had a presentation. They left it behind. So question about a mirage. Again, it's caused by that heating. Now in the atmosphere, remember we talked some in the last unit about the sunrise and sunset, right? The refraction in the atmosphere, the light in the atmosphere. Now the reason you see a sun, ever notice like the moon and the sun, when they're close to the horizon, they look much bigger?
Yeah.
Well, we'll have to. Yeah, it's hard to predict.
What?
But if you go to the coast when the sun's going down, now when you see that great big moon, that great big sun, like if you were on the San Mateo coast, you saw that big sun, the sun is actually set already. The sun is actually below the horizon. But because of refraction, again, because of the refraction, it appears the sun is higher up. But it's bigger. You know, in fact, you know if you see the sun really big, you know the sun is actually below the horizon. In fact, as the sun goes down, you even kind of see it. It's kind of small, then it will start getting like bigger, bigger, bigger. And what's nice, you can actually see this one because of all the atmosphere. You can look at this one because you're not really looking at the sun. Happens in the morning too. This great big sun will come up out, especially like in the ocean, will come up out of the ocean, and it'll start getting smaller. And all of a sudden, this little sun will kind of come right out of the top of it. On that. Of course, we can't see that. If you're ever like on the East Coast, you know, you can see that coming up in the morning on that. But it works the same way with the moon. That's why we had that moon. But remember, we talked about that last unit. This is what gives us that red sun, the reflecting, along with our next topic, which is dispersion. Dispersion, because the bends, that blue light comes out, and all that's left is the red. So it's all this refraction stuff going together. Which leads us to dispersion. We talked about spectra, but we did not talk about how we got spectra. Right? We didn't talk about how we got the spectrum. We just talked that we have a spectrum. Dispersion is how we get a spectrum. This is that separation of light into those separate colors, frequencies, spreading it out. And it's caused by the slowing of light and a change of wavelength. Frequency does not change. It also has to do with going around sharp edges, you know, different ways will bend different amounts. Basically what happens, the higher the frequency, the more it bends. You know, basically high frequencies, small wavelengths bend more than low frequencies, high wavelengths on that. So what color is going to bend most in our visible spectrum? Violet. So violet, blue and violet bend the most. Red bends the least.
What's the difference between purple and violet?
Usually in physics we say violet rather than purple. I don't know if there's a art, and I don't know if in art, if you got violet and purple, if those really represent different colors. But in physics, we usually don't use the word purple.
What's wrong? You just don't.
I'm just saying that the proper physics word for that color is violet.
Because purple is slang. Hearts.
We use the V word, not the P word.
P word.
What? Physics is made up.
Physics is
It just explains how the entire universe is put
Oh, I
together.
thought you said space.
Who needs the entire universe?
Yeah, I believe it's space. That's
No,
what
this is completely made up.
You could believe that, but you'd be wrong.
No, only if like you try to prove it wrong, but it depends on your belief.
Believe me, no matter what you believe, energy is conserved. Believe me, and no matter what you believe, if you step off the rail of the Golden Gate Bridge, you are going to go down. No matter what you believe in, you are going to go down and hit the water. This is one thing about physics. Physics is a very equal opportunity thing. It doesn't matter who or what you are. You guys are all going to accelerate at 9.81 meters per second squared, regardless. All right. Anyone need more time? I hear a lot of chairs, so I guess you're done. So, guys. So we look at this. Now, you might say, well, why don't we get that through like a window? Window is glass, just like a prism. Has nothing to do with the glass. Has to do with the shape. Notice a prism has a triangular shape. A window is rectangular. Now, when the white light does go into the window, when it goes into the window, does it get bent in the glass? Yes, it does. Does it undergo dispersion? Yes, it does. In the glass, you're going to get these, they're going to basically get separated just a little bit. But remember, we talked about this last time, when it goes in at a certain angle, it's going to come back out at the same angle. So when it comes out again, it all gets put together again and is back into white light. So technically in between, yes, it undergoes dispersion. But because we made a turn to the right and then a turn to the left. But here we make a turn to the right and another turn to the right. So it doesn't get put back together. So we make 1, 2, like that, it gets separated. But notice our blue light gets more than the red light. The other colors are going to be in between on that. I have a little video. A little thing here that kind of shows. Oh, that's more of a picture. So you can see the red wavelengths, which are longer, bend less than the violet, which are shorter wavelengths.
Oh, that's not bandage, is it? Like a t-shirt.
Now, total internal reflection. Now, this only occurs, I want to add that word only, occur when going from a slower to a higher speed medium. Higher to lower. In other words, you go from a higher to lower in this refraction. So in other words, water to air, glass to water, glass to air. Never air to water. Never air to glass. Never air to diamond. Diamond to air. Okay? And you've experienced it. Ever had a case where you've looked in a fish tank at the right angle and it looks like the other side is a mirrored surface?
Yeah.
You're getting total internal reflection because glass has a higher index of refraction than water. So as the air, if you're going from the glass to the water, you're going to get that reflection and so on. And if you look, and what it means is, remember we have our formula, Snell's law. Our refracted angle is 90. So we talk about this angle. This angle that you reach is called the critical angle. We sometimes give it a theta c. In other words, when I go in at theta c, the refracted angle is going to be 90 degrees. When you're trying to find the critical angle, you know, oh, 90 degrees. But remember, only like water into air. So we see as we're going across, see how the angle, the refracted angle, it happens because remember, we're going from a higher speed to a lower speed, we move away from the normal. So eventually we end up going right along, like that. We go along the edge, that 90 degrees. So this would be my theta c, my critical angle. When I go beyond that, it reflects inside. It reflects inside, like that. And we use that property in a lot of optical devices. Anyone need more time? So we use this in a lot of optical devices. Like if I put two prisms together, light will come in, it'll do a total internal reflection, come down the second one, and I can change the position. A lot of optical devices that you might think are actually using mirrors actually use prisms. Like little kitty binoculars and little kitty periscopes. They use mirrors. You took it apart, it'd be mirrors. But if you have regular binoculars, you have good binoculars, they don't use mirrors, they use prisms. So usually you have the larger part of the barrel, and then it's going to go into a smaller part that you look through together like this. But you're going to have some sort of prism. Basically, let's see, kind of like that. You have another one that's like that. So when you look through it, it kind of goes across and out that way, like that. It's kind of working like that. Going across, so you have two sets of prisms. We use prisms because they're a little more durable than a mirror. With a mirror, it's very easy to get out of alignment. It's a lot harder to get the prisms out of alignment if you jostle it, things like that. Periscopes on submarines, you have big prisms. You have big prisms that they use to go up and above and things like that, multiple things like that. Now, total internal reflection here, the diamond. Diamond has like the highest index of refraction. Has like the smallest critical angle, like 24 degrees. Water is about 48. Water is about 48 degrees. In other words, you can see out, if you look at an underwater pool and you look up, you can see someone on the deck if they're right above you. Out to about 48 degrees on either side. But if it's beyond 48 degrees, ever notice all you see is like, it looks like the bottom of the water's mirror. What you're actually seeing is the bottom, because the surface is usually rough. You don't see that nice image. You can't see it, but you can't see someone standing over in that part of the pool on the deck. Diamond is even more. This is one of the reasons when you get a diamond, is it usually embedded inside of a gold ring, or is it like on little prongs, real open? So on the prongs real open, you think, well, that's kind of dangerous, you can lose it. Well, if you embed it in the gold, it kind of loses the purpose of doing this. Because what happens is the reason why they cut all these facets in it is because all the light that goes into it from whatever direction bounces around on the inside with total internal reflection, and basically it all comes out the top. So all the light that comes in the sides, eventually it will come out the top, which is why you have the big flat surface on the top, which is what makes the diamond look so brilliant. This is what makes diamonds valuable, these white diamonds valuable, because they're not intrinsically very uncommon. Well, no, diamonds are not very rare. And not like other gemstones. Other gemstones are much rarer. Diamonds get good marketing, but it's this quality of diamonds that make them so beautiful because they just are so brilliant and things like that. Yes, ma'am.
So if they put a lot of cuts in it, it's just sparklier?
Basically, the facets are designed to internally reflect the light out the top. That's why the facets are ground into the diamond, is to cause total internal reflection, so it goes out the top.
That's why you work.
They don't come out of the ground looking like this. Well, they kind of look like, if you've ever seen a piece of quartz, they kind of like, and I think natural diamonds, I think, have a kind of a cubic shape to them. I mean, naturally they have kind of a cubic shape to them.
How about cubic zirconia? It's like the same though.
No.
It's different.
Oh, believe me, it's not the same.
No, it's not as hard as a diamond, but like it looks the same.
Little ones do, big ones don't.
Oh, really?
I mean, yeah, little ones you can fake deal. Little ones, they have to use microscopes to tell the difference. Big ones, there's a lot of difference. you know, in how they look. If you had similar cubic zirconia and diamond together, you'd be able to tell, okay, this one is not as nice as this one on that. So you can kind of see internal reflection. They're kind of moving. He's moving the ray. It went through. They kind of see how it bounces on the inside of the water. Bounces off the inside. On that. So you can see he's moving this little ray of light over. Kind of gets through, but as it gets the critical angle, see how it bounces off the top of the water. It's coming in the tank. It's bouncing off the top. That's what he's just trying to show there. Fiber optics. Fiber optics work like this too. The little instead of big giant cables, now we have basically spun glass tubes, and they use lasers, and the laser light just bounces down the inside of the tube. Doesn't matter what angle the fiber optic is, but this is what allows them to put a lot more information in a much smaller space. And so you can see from this guy, see, no matter how he twists the cable, does it affect how bright the little end light is there? You know, it just goes through his fiber optic, which is good. This is the kind of stuff they shove down your throat in other places to go see your insides. Well, to see the inside of your body, they really have two options. They either go down this way or up the other way.
What other way? Oh, that way?
Well, usually that requires surgery. But they're either going to put it down your throat or put it in the other direction. Put it at the other end. Remember, your mouth and the other end, there's a tube. It's kind of an enclosed tube all the way through, and they're gonna go through either end, whichever end they decide they're working with.
Can't they use it for surgery, like when?
Oh yeah, they do that too. All right, so we are done with this. Shh. We are done with those. That hand up or a stretch? All right, so let's talk a little bit about the concept of it. So this is what you are working on the rest of the period. When you finish these, before you put it in the box, you show me that you have completed this. All right? Shh. All 3 pages. It's really not that difficult. You may work with a partner. Did I do all this before people start running around? You will need the ruler. You will need the rulers when I'm done. All right, Stephanie, now. You may work with a partner. You may move to be with that partner. So the first part here, they're working on the law of reflection. Look up here, everyone. Eyes. I want eyes, or else you're going to be. I don't understand. You're doing the law of reflection. Remember, the angle in equals the angle out. You make them normal on these things. Down here at the bottom, you notice the angle of incidence is different. So when you make your reflected ray, they want you to backtrack that reflected ray and see where they intersect. Do they intersect like that? Same idea with the curved mirror on the other side. Now we said that a curved mirror, if it's at the focus, it will all come out straight. And all that straight, does that go by the law of reflection? Are the angles actually equal? Think about that when you're answering that bottom question. Now this one, I'll do the middle one here in a second. 29.3 is about refraction. You're drawing in rays. And you're answering these questions about the fish. This is about the total internal reflection. Remember, there's a value. There's a degree angle. You need to look in the book or something to find that degree angle for the critical angle. It has to do with whether he's going to see the guy or not. So you might want to go look up that value in the book. Now, I don't need this. The thing about Abe in them. Look at the middle sheet. You have Abe and all these other people. Abe and all these other people. And you want to know, do they see each other? Now the very first one, you have Abe and Bev. So you have Abe, and you have Bev, and you have a mirror. And we want to know, can Abe see Bev? Now how you do all these is, where is Abe's image going to appear to be? It's going to appear to be on the opposite side. So what you do is you put where their images should be. So if this is 1 inch on this side, it's 1 inch on that side. And basically you put your straight edge down. So in order for Abe to see Bev, this would be Bev's, we put our straight edge down, And if the line between Abe and Bev's image crosses the mirror, can he see her? Yes. But there's another section. It has a little mirror, and you have all these people. And they want you to see, like Abe. Abe is down here, and you have B's, all these B, C, D, notes are all in alphabetical order. You need to know, can he see Bev? Can he see this person, this person, this person? So what you want to do, just kind of take your straight edge and extend past that mirror. And just like you do here, we're going to put, there's Abe's image, there's Bev's image, and so on. So like for this person, I put my straight edge down. Can he see this person right there in the mirror? No, because did it cross the mirror? Nope. Can he see that person? No, because the mirror is the solid line. Can he see this person? Yeah, because it crossed the mirror. You don't have to draw in all of them and draw yourself crazy drawing all those lines. You just have to put your straight edge. So you check A looks at B, C, D, E, F, G, does it cross? And you write down at the bottom. And you do the same thing for each person.
For the first one, you measure from the middle there.
Kind of. Now, if you notice on the back side, they have the same thing, but now they're farther away from they're different distances from the mirror. So however farther from the mirror one side, they're that distance on the other side, and so on. All right? All these need to be done by the end of the period. Show them to me. This is your ticket out of here. All that. Okay?
Okay.
Get to work. Like I said, you may work with a partner, no trios. Singles or partners. And you can work with any partner you want to. You may move and work with any partner you want to. But you